morning, everyone. Thank you for joining us today. First of all, I'd like to thank all of you for attending this session this morning. And I'd also like to thank our partners, CanBIM and SaskBIM, and all of the annual sponsors that participate. My name is Erica Morris, and I work with Building Point Canada. I'm an account manager there, and Building Point Canada is one of the annual sponsors, and we're very excited to be part of the CanBIM group. We believe in helping companies and people with technology in the construction industry. And so we're very supportive of CanBIM and everything that they're doing. Now, I'd like to point out a few housekeeping issues with the system. There's a few buttons that I'd like to highlight for you. There's the chat button. Now, the chat button is for any of the attendees to participate in conversations with each other, so everyone can see what goes on in the chat. Now, there's also a Q&A button. Now, this is for questions. So if you want to ask any of our speakers any type of questions, then you can put your question under the Q&A tab. Now, if there's multiple questions in there and you have the same one, you can vote and you can hit a like on a question, and that kind of brings that question to the top of the list to be asked to the speaker. So that's the chat and the Q&A. There's also a handout section. So any of our speakers that have handouts, you can find handouts that you can download from the handout section. Okay, so let's get started with our sponsor speaker. I'd like to introduce to you Mohit. He is one of my colleagues and my friend, and he's been working in the field of BIM and field technology for over 10 years. So Mohit, welcome. I'm going to pass it over to you.
Thanks a lot, Erica. Good morning, everybody. This is Mohit. I'm one of the account managers here at Building Point as well, and based out here in beautiful Vancouver, BC. So good morning to you all, and let's get on with this presentation. So Erica and I both represent Building Point Canada. So we are Trimble channel partner for Canada. Our portfolio basically covers everything that Trimble Solutions has to offer in Trimble Buildings division. So we have tools that cover the design, detailing solutions, all the way to the mixed reality, field capture, field layout solutions, and onwards to project management solutions. Trimble itself has solutions right from a building concept all the way to building construction to complete the full life cycle of the building. So concept to reality and onwards, all the way from facility management, so on and so forth. So the big thing for us at Building Point and at Trimble is the connected construction idea. So we want to have, we've all seen beautiful BIM models containing a lot of information, a lot of detailed information that can be used downstream and should be used downstream all across the construction life cycle. So the big push from us is this connected construction that bring this information forward all through the construction stages and build from the model, build with the model. So of course it all starts in the office with a great model. So it's you put all this information into a connected model, all the parametric information, everything that is to be built should be incorporated into the model itself. And that same model then gets pushed onto the fabrication stages. So it can be used for shop use to create pieces, to create parts, for fabrication, for assemblies, things like that. Now, what happens after that is sometimes that information does or does not make it to the field in its entirety. And that's the big piece for us, where we want to make sure that this information and regardless of what tool it gets created in from your authoring tool, it does translate all the way down to the field, the construction site. So to make sure that all this information, the connected model, the complete information, the parameters, everything kind of gets trickled down. So some ways in which that can be achieved is by using robotic total stations and such. So bring your point information, bring your layout information all the way to the site, and then the pieces start to kind of come together. from there on, we encourage the use of 3D scanning so that you can kind of verify, check the construction progress versus your models, make sure that there are no clashes, there are no emissions, things are going as planned. There's not much missing out over there. There are several tools in our portfolio. My favorite one is Trimble Connect, that kind of allows this complete collaboration all the way from the information that sits in the model and how that can be shared across disciplines, across companies, across stakeholders on the project, so that they can all share information, not just model information, but content information. And this does not have to be a one-way process. This is a two-way street. So the big push is not to work in silos, but kind of work with everybody and kind of make it a team approach. So over here, the information from the site has kind of traveled back into the 3D model. So we mentioned 3D scanners. So as during construction stages, you can scan for information, and that information kind of comes back into the models, and we check against the model to make sure that, hey, we're not missing out on stuff, or there are no clashes per se. So on this slide, you can see there are some clashes and something like that can be found out pretty early on, and corrective actions can be taken. And as we go through the process, voila, you have a beautiful project completed out of that same information that you started with. So the big thing from us is work in flux. Don't work in a silo. Take the information straight from modeling through execution to the site, bring it back into the model, and complete the full workflow. We have various tools that can assist with that, and the big push from us again is build from the model, constructible model. Take the information with you to the site. We are always excited to chat about that, and please do reach out to us. Myself or Erica will be more than happy to engage in this discussion. Over to you, Erica. I'm not sure if you had any questions for me.
And the scanning. Can you expand on that for us?
I'm sorry, Erica, we lost your audio there. Can you
hear me now?
Yes.
Okay. Can you just expand on what kind of software is used for the total stations as well as the scanning?
Yeah, so the tool that that drives both the scanners and also the total station is Trimble Field Link, which kind of is capable of taking the 3D models directly, importing them as IFC files, as drawing files, kind of bring them into the tablets, into the handhelds that can be taken on site for construction layout, and the same software can be used on the scanning end as well to kind of capture that same information, verify against the model, and bring it back to the office.
Okay, that's great. Thank you, Mo.
Well, thanks very much, and over to you.
Okay, thank you. Now I'd like to introduce our next speaker. So his name is Tristan, and he's currently the Building Performance Analysis Lead at Intuitive. Now, Tristan leads the Advanced Performance Analysis team and has been engaged in the world of sustainability and design. He applies his talents to improving the energy efficiency of our built environment. So he's contributed to the design of some of Canada's highest performing building projects, including the country's own certified living building. Now, Tristan is a licensed engineer in the provinces of Alberta and Ontario and is certified by ASHRAE. He's also a washed up former rugby player that loves the Ontario backcountry. So Tristan will lead us on a journey into sustainability and the digital built environment.
Thanks for that introduction, Erica. Can you hear me okay?
Yes, I can.
Excellent. So welcome all to our discussion of sustainability in the digital built environment. I'm really hoping that you find it informative and that it helps expand on some thinking around the importance of sustainable design approaches at all stages of the design process. I also hope that it helps to illustrate some of the exciting work that design teams are undertaking to address the wicked problems of climate change through digital methods. So my hope is that through our session today, you'll gain a broader understanding of the role that both embodied and operational carbon play in mitigating climate disruption. And I'll also be presenting some of the potential design strategies and analysis techniques to enable design for minimizing total project carbon. For those of you who aren't familiar with Intuitive, we're a multidisciplinary firm with primary focuses in structural engineering and building envelope sciences. We pride ourselves on being creative, collaborative, and advanced in our approach, regardless of what problem we're trying to solve. And our one company philosophy allows for cross-pollination of ideas between firms, or between teams, disciplines, and offices, which means that when you're working with one of us, you get to tap into the collective brain trust that we have spread across all 7 offices in 3 countries. So a quick agenda just to lay out where we're going to go for with this presentation. I'd like to start with a call to action to set the stage for why this issue isn't just an important topic, but in some ways the most important topic facing the design and construction world today. Then we'll dig a little deeper into the worlds of both embodied and operational carbon and how they can be assessed through the design stages. After that, I'm going to be presenting a few case study examples of different digital approaches to sustainable design that we're working on right now to address these issues on our projects. So first, we'll look at ways of reducing embodied carbon in the design process. Next, we'll look at ways that the more traditional energy modeling workflow can be adjusted to minimize operational carbon. And finally, we'll look at a couple of exciting initiatives aiming to revolutionize how we approach the decarbonization and rejuvenation of our existing building stock. So part 1, a call to action. Climate disruption is a real thing and a massive problem facing humanity as a whole. Our house really is on fire, and it's important that we begin to act with an appropriate sense of urgency. It has been generally agreed upon that within the next 10 years, the global economy needs to massively reduce the greenhouse gas emissions associated with economic activity in order to have a hope of not locking in a series of feedback mechanisms that will amplify our own climate impacts. To be frank, nobody has a clear idea of how this is going to play out. It is, however, widely accepted and recognized that no one industry, nation, or group can bring about change on this scale. It will need to be a collective effort across all branches of the world economy. Think silver buckshot instead of a silver bullet. Now, in Saskatchewan, Regina particularly, this will, from a purely weather perspective, this means that the average annual temperature is going to continue to rise through the remainder of the century. I'd like to point out that the data on this slide and the next couple of slides comes from the Climate Atlas of Canada website, climateatlas.ca. I encourage all of you to check it out and become informed of potential climate impacts in the areas where you design. A similar trend presents itself for very hot days in southern Saskatchewan, with a statistical increase expecting to see the number of very hot days triple by the end of the century, and with worst case scenarios looking at a 5-fold increase of these weather conditions. Now, looking at this data in a broader perspective, you can see that each of the design criteria associated with space cooling are expected to increase significantly. And the extra kicker is that it's not like the heating metrics are shifting upwards with anywhere near the same level of magnitude. So from a design point of view, this means that the conditions that we need to account for are expanding to include increasingly divergent heating and cooling design temperatures. So if you're hoping that climate change would bring an end to harsh prairie winters, you're probably out of luck. But you can expect that your summers will get hotter and have substantially more intense storms. I'm hoping at some point you've all seen plots like this of some kind. These next few slides are borrowed from our colleagues at Mantle 314, who Intuitive has been working closely with to gain a deeper understanding of embodied carbon and upcoming carbon policy. These 2 plots represent the GHG emissions reduction targets necessary to avoid the worst impacts of climate change. On the left is data for the world, and on the right is for Canada specifically. Both plots share the same basic trend, requiring an aggressive approach to reductions in the coming decade after an assumed peak this year. Both plots then present continued reduction towards carbon neutrality in 2050. It's important to note that the aggressive reductions to 2030 assume that all new construction will be carbon neutral by that point. If you practice in Toronto or Vancouver, you will have noticed energy codes that are already in place and driving towards this goal. And in other jurisdictions, you can assume that the National Energy Code for buildings will not be far behind. It is safe to assume that no matter where you practice, the building code in your jurisdiction will have reached a level of stringency to demand the design of all new buildings be net zero for carbon by 2030. These targets also assume that the entire built environment, whether new or existing, will be carbon neutral by 2050. This was the impetus for cities like New York, who recently implemented Local Law 97, requiring operational carbon reductions from existing buildings that are enforced with steep financial penalties for those who don't comply. Similar programs have been announced and are soon to launch in Washington, D.C. and St. Louis, Missouri, and you can anticipate that they will begin making an appearance in Canadian municipalities soon. It's also important to remember that a new building becomes an existing building the second it reaches occupancy. So designing to a standard of anything less than net zero carbon today is really just setting up the ultimate building owner for a hefty retrofit bill sometime in the next few decades. Now, there's a big reason why so much focus is put on the sustainability of the built environment, and that's that we're a big part of the problem. Roughly 40% of total global greenhouse gas emissions are associated with the construction, operation, and demolition of buildings. All this is to say that none of this sustainable design stuff is particularly optional anymore. Net zero buildings are no longer niche or only for the leading edge projects. They are no less than a necessary ingredient for the human species to continue to thrive. So we have a long way to go in a short period of time, which is a really awkward problem for the design community, as architecture, not unlike yoga and the law, is a practice. And it might seem like semantics, but in this case, the words used really matter. Design of buildings is a body of knowledge that is based on repetition and informed by past precedent. But we don't really have precedents to work from when it comes to a carbon neutral, normal building. Changes to required design approaches have come on so rapidly that folks like me, who really aren't that far into our careers, have more or less seen all of the rules completely rewritten. So how are we going to get there? Hopefully, given the M in CAN-BIM, it shouldn't be too much of a stretch to realize that I'm going to advocate heavily for a model-based approach to inform our designs where we can't rely on precedent anymore. But in pushing for a modeling-based approach, I always like to bring up personal hero, statistician George Box, who is frequently credited with the most important thing to remember when using simulation to inform a design process. That is specifically that all models are wrong, but some are useful. I'll throw in a few reminders, but please try to keep this in mind as we work through some of the case studies, that the goal of analysis isn't always to identify the absolute correct answer, but to give guidance that facilitates decision-making. So now that we've framed just how massive the problem is, and why the design and construction industry needs to be a part of the solution, I'd like to give a little bit more explanation of embodied and operational carbon emissions so that we can see how they relate and the nuanced difference between the two. And hopefully this will put us all on an equal footing going forward as we look at the details of the case study. So we saw some similar data presented a few slides back, but it's worth highlighting again that the construction, demolition, and operation of buildings accounts for just under 40% of global greenhouse gas emissions. Digging a little deeper into that number, it is currently about a 3-to-1 split between operational and embodied carbon. Operational carbon being the GHG emissions associated with the energy consumed to operate a building. This is the carbon emissions that we're all familiar with. It's associated with operating the local electrical grid, as well as any fossil fuels, typically natural gas, consumed for space or water heating within the building's property line. Depending on how that local electrical grid is fueled, very similar designs can have vastly different operational carbon impacts, which is why the industry is pivoting to start focusing more on carbon than on energy efficiency, as had previously been the case. Embodied carbon is a much more nebulous concept, and it's the emissions associated with the extraction, processing, manufacture, transportation, installation, and demolition of all materials or components that make up the building. It's essentially the emissions associated with all the stuff that make a building what it is. Whole life carbon or life cycle carbon is a term that captures those total emissions associated as just a lump sum. And it's good to remember here that this total number is really what we're aiming to reduce, and that the physics of our planet's atmosphere really doesn't care how these emissions are classified. This diagram is also courtesy of our partners at Mantle 314, and it helps to illustrate this breakdown a little further. The operational carbon piece really only exists inside the purple box in the middle of the slide, while embodied carbon emissions can occur throughout a building's life cycle, even through ongoing maintenance during the operational phase. Now, embodied carbon has been getting a lot of attention recently, and for very good reason. I previously mentioned that there's about a 3-to-1 split currently between embodied and operational carbon over a building's life cycle. So the plot on this slide illustrates this by plotting the accumulated carbon for a project over time, roughly illustrating a building that was built that we would have built recently until more stringent energy codes started coming into place. So at the far left, you have the opening day of occupancy, and at the far right, you have the closing day before demolition. As you can see, the embodied carbon debt is all accrued as the project is being built, and operational carbon adds up over time depending on the energy efficiency of the building's operations. Looking at this, it's pretty clear that historically, operational carbon was the most important thing to address to reduce a building's environmental impact. Now, if you look at the cumulative emissions associated with today's high-performance buildings as mandated through those increasingly stringent building codes, you start to notice that as operational carbon is reduced through energy efficiency, the embodied portion becomes far more significant. In this way, buildings built today will likely see more of a 50-50 split between embodied and operational carbon over their life cycle. And finally, given what we know about the need to reduce emissions rapidly in the next decade, we can see that embodied carbon makes up the lion's share of the carbon debt accrued by a modern building in its first 10 years. This next slide is another way of looking at that same issue. As operational energy consumption decreases and electrical grids decarbonize, embodied carbon becomes the primary source of emissions in the building sector. So hopefully, I've successfully made the case for why looking at embodied carbon as part of your design process is important. But what can we do about that? So I'd like to introduce you to Carbon. Carbon is our in-house tool that has been developed for evaluation of embodied carbon in the early phases of the design process. We like working the letters EN into everything we do at Intuitive. You just kind of get used to it. But I apologize for the pun. I'd also like to apologize in advance to any structural engineers listening in on the presentation, as this is not my area of expertise. So I'm going to do my best to stay in my lane on the technical aspects of structural design while still giving you an idea for what the tool can do. So in a nutshell, the tool accepts architectural concept inputs from Rhino, and then uses built-in smarts to build a concept level structure to compute material quantities. Total embodied carbon estimates are then based on one-click LCA and EC3 databases. This helps to bypass the fact that a detailed structural BIM model is rarely prepared until much later in the design process. I want to point out here, though, that this tool, it shouldn't be confused with tools for detailed structural analysis like SAFE, RAM, SAP 2000, or ETABS. And so from a structural design point of view, you might say that this model is wrong, but from an embodied carbon angle, it is incredibly useful. The examples that I'm illustrating in the screenshots here are for a concrete structural design. We have a similar module for steel schemes, and a mass timber module is in progress. The tool accepts up to 10 use cases for a building where different floors or groups of floors would have different loading conditions. This is great for the modern mixed-use retail office condo building typology. And after determining a concept level structure, Carbon then allows adjustments to key structural elements, such as column layout, shape, number of steps, and what floors those steps occur. Once inputs are confirmed, Caramba is run in the background to apply total loading to a membrane mesh, applying the loads to the columns and the core. And from here, the tool back calculates what the total column dimensions and material quantities are to calculate the total embodied carbon. There is a core tab where you can custom size and place your core to influence the structural calculations, but the core tab itself doesn't do any structural calculations. So it's important that dimensions and locations for your building core are realistic for the type of design being examined. The core tab still feeds back to the columns calculation, as there are no columns placed within the area defined for the core. There are similar tabs for both slabs and foundations that take almost the same tack as the columns tab, where they take user inputs in terms of structural design preferences, and then calculate in the background what the required slab or footing dimensions and material quantities will be before calculating total embodied carbon. The tool also includes a cladding tab, which allows you to select cladding system. There's a couple reasons for this. Cladding choices tend to have a high can have a high embodied carbon content themselves, and also apply to the loading calculations and the total weight of the building, so can influence the embodied carbon of the structure as well. The tool allows assigning multiple cladding systems applied as a percentage share of the total facade area. And at the end of it all, the tool provides outputs for embodied carbon by material type or element type, as well as by use case or by floor. I'm particularly fond of the element type results because these can be very illustrative at helping design teams to know where their efforts can have the greatest impact. You know, is the most embodied carbon in the slab, or is it in the foundations? And while not instant or real time, the tool is relatively fast compared to building a complete detailed structural BIM model, and it is fast enough to allow answers that can allow for optioneering of different structural approaches based on a desire to limit embodied carbon at the earliest stages of design. So now we have a tool in our toolbox that helps us look at embodied carbon, and I'd like to flip it now and have a look at how we can influence operational carbon through the design process as well. So you'll notice a similar trend when it comes to looking at operational carbon, in that to properly address it, it requires early involvement by an analysis team before aspects of the building design become locked in. The image on the slide here is of the McLeamy curves, which represent the inverse relationship between the effectiveness of design changes and their cost of implementation as a design process progresses. Traditionally, the analysis of a design's energy consumption was held until late in the design process, when it felt that there was enough information that an accurate energy model could be prepared. But given that we all know that all models are wrong, striving for an accurate prediction of final energy use has always been a bit of a fool's errand, certainly in the design stages. There has been a lot of ink spilled in recent years about the so-called performance gap, which completely misses the point of what performance simulation is best suited to do. And by pushing any modeling out until later in the design process, the results that come from that modeling process have limited ability to influence the actual design, which leaves a lot of opportunity on the cutting room floor. I'm hoping that some of you have seen some variant of this sustainable design pyramid in the past, but I'd like to come back to it as it presents a 10,000-foot view of what our design approach for high performance buildings needs to be. Traditional takes on sustainability have often flipped this upside down and kind of worked the pyramid from the top. In the worst case scenarios, this was a business as usual building, getting some solar panels put on the roof for a green power purchase agreement that was made to offset the impacts of an otherwise poor design. Much more common and indicative of sort of the first generations of LEED was the attempt to engineer our way out of a design with the application of high-end mechanical systems and controls to limit the energy consumption required to meet the heating and cooling demands that were locked into a design based on its form and opacity. Where we really need to start in our design process is to start thinking passively first. Design parameters like window to wall ratio, floor to floor heights, massing, and orientation of a building are often decided early in the design process without any specific considerations to performance and really only looking at programmatic needs and desired aesthetics. The design question needs to become, how can we design spaces that need active conditioning for mechanical systems for as few hours as possible each year? Ditto for lighting systems. How can we maximize the energy provided by the sun while it's available? Analyses to support this can look at issues such as daylight and glare avoidance, modeling how design decisions around window placement and area can influence both good and bad solar exposure. And as focus shifts to a building envelope that is far more substantial, there can become a point where perimeter mechanical systems can be greatly reduced or even eliminated. A simulated approach looking specifically at thermal comfort can help assuage concerns about the effectiveness of how a space will feel without mechanical conditioning. This can help keep projects under control by limiting the amount of redundancy or belt and suspenders approach that needs to be made in a design. The same can be said of natural ventilation. Analysis of local climate patterns and prevailing winds can help inform strategies for how openings need to be placed in order to drive the required amount of fresh air into a space. I anticipate that the attractiveness of natural ventilation approaches is about to have a bit of a resurgence in a post-COVID world. And sometimes eliminating strategies can be just as useful as knowing which ones to pursue. A climate or site analysis might point to favorable natural ventilation conditions during shoulder seasons in Regina, but it would be an entirely different story in Atlanta. An approach that we like to take in the earliest stages of design is shoebox or simple box modeling. This approach reduces the need to have a set form for a building, but instead looks at key design parameters like space type, gross floor area, number of stories, and intended form efficiency to build a model that is representative of the concept to be pursued without actually being accurate to its final form. This then allows rapid iteration of various envelope parameters such as window type and area, levels of insulation, floor-to-floor height, and to determine what limits there are on an envelope's performance for specific design goals. I like to think of this as like providing design bumpers, like when little kids first learn to 10-pin bowl, to keep the design on track down the middle of the lane towards its high-performance targets. And again, while the absolute performance outputs of this type of model will be wrong when compared to actual utility bills, the comparison between design cases is incredibly useful for knowing where the design needs to go. Because of the simplicity of these models, it can allow us to run lots of them, ideally launching them iteratively via algorithm. It is currently de rigueur to present this wealth of data in using a parallel coordinate data representation, where each thread represents a single model iteration, and each parallel axis can be limited to reduce the number of results displayed. There are a lot of these tools starting to crop up from consultants, but it's important to remember that they all do essentially the same thing, to not get lost in the spaghetti, and that it really is there to help you hone in on your design process. My personal favorite is a free web-based tool called Design Explorer that was initially developed by Thornton Tomasetti out of the States. So hats off to them for putting a great tool up that's free to use for everyone. Similar parametric approaches can be taken for all manner of early stage simulations. The image you see now is a still for some work we did for a project that had a large main floor workshop area that the client was hoping to cool passively during summer months. What is illustrated is the output of a series of iterations for how much solar heat gain is received by this space with the shop doors open with varying overhang depths to determine if a passive cooling approach was viable. And in the next case, you'll see that we're illustrating an algorithmic approach to window size and placement to minimize glare in an open office area. I apologize, both of these images are GIFs depending on the presentation format, but we're gonna have to live with them as stills for the moment. And for both examples, it's important to note that they both only focus on a portion of a building, with the answers that are obtained then applied more broadly throughout the entire design. So in some ways, this method is akin to digital prototyping, but specifically around building performance. And so finally, moving towards that ultimate goal of a carbon neutral built environment by 2050, we tear down and replace very few tall buildings. So there's a real need to reconcile how to get a wealth of existing building stock that was designed long before any standards for building energy efficiency were in place to a level of carbon neutrality to avoid those worst case scenarios of the climate crisis. This is especially important as an existing building typically incurs far less of an embodied carbon debt in its retrofit than when constructing new, particularly if the structural systems are maintained. So these next few slides are going to give a glimpse into some research that was undertaken by Intuitive and the University of Waterloo, looking at generative approaches to overcladding of post-war residential towers. I'd love to take a deeper dive into their methods and results, but unfortunately, their research hasn't been presented at the conference that it was developed for, and I don't want to give any spoilers. So I'm just going to have to give you an overview of the approach that they took. Their existing building was first rationalized, and then configurations of different modules that could be built outboard of the existing structure were tested. These configurations were analyzed for daylight availability, life cycle carbon, and heat energy for all possible configurations of models. An optimization approach was then taken to identify the cases that had the lowest life cycle carbon as well as the lowest structural complexity to identify an appropriate set of solutions. And then the inclusion of simulation for daylight and heating energy allows those elements to be used to select the preferred option from this subset of optimized candidates. Pardon me. And moving on to digital twins. From what I've seen from recent CanBIM presentations, the digital twin is not an unfamiliar concept for this audience. And while I have seen a lot of exciting approaches to digital twins for managing risk, construction complexity, as well as digital prototyping, they also have a significant application for reducing energy consumption and the associated carbon emissions in the existing built environment. So in a nutshell, a digital energy twin leverages an existing building energy model to provide the physics and heat transfer calculations to fill in the gaps that can exist in sensor data. And as the cost as Internet of Things sensors has continued to fall, we're able to extract far more data from an existing building to complement the high-level bulk information that was presented by utility meters and building management systems. So having this accurate real-world data allows the digital twin energy model to be tuned to replicate past operation under actual weather conditions. Ideally, this model is actually getting close to not being wrong. The image on this slide is from IESVE, who have recently launched a tool called iScan aimed at helping to bridge the gap between recorded sensor data and simulated results. This first step of tuning the existing model often identifies areas of low-hanging fruit where energy was already being wasted and can make a clear case for shallow retrofit. But the real power of a digital twin environment is that it introduces an accountability approach through ongoing measurement and verification of savings that can be used to help secure retrofit financing. This ability to secure financing for this type of deep operational carbon intervention has really been a stumbling block for many existing building projects in the past, as the upfront costs to achieve the kind of carbon reductions that we need to see tend to far outstrip what exists in a typical maintenance budget, while still having a reasonable financial payback when looked at from a financing point of view through a bank or a bond. So with that, that concludes my presentation for today. I'd like to thank you for your time and attention and open up the floor for any questions that may have come in while I was speaking. I'd also like to say a big thanks to our sponsors, CanBIM and SaskBIM, as well as to my host for helping to set this up. So back to you, Erica, and we can start looking at any questions that may have come in.
That was great. We do have a couple of questions I'd like to maybe address. Can you hear me?
I can.
Great. Can you just dive a little bit deeper into, why we need to address embodied carbon in construction as quickly as possible?
Yeah. So I mean, that really all ties back to a concept that's sort of being referred to as the time value of carbon. I'll bring up this slide again. So with the idea being that carbon that goes into the atmosphere today makes its warming impacts right away, and that as there are global feedback loops that increase warming can beget more warming, the earlier a carbon molecule reaches the atmosphere, the more potential impact it has to cause. So when you're looking at embodied carbon, that whole debt is incurred pretty much as soon as the building is built, and there's no opportunity to take it back. Whereas when you think about operational carbon, I like to say that your HVAC may only last 15 to 20 years, but your envelope tends to be forever. So there are ways to intervene to increase the operating efficiency of a building and reduce that operational carbon slope over time. But really, once you've incurred that embodied carbon debt, it's there, it occurs, and like money, it starts to accrue interest in the form of knock-on climate change effects. So it really is a pertinent approach to address it as quickly as possible.
Okay, thank you. Just another question here. You also mentioned the need to begin modeling and simulation work as soon as possible, as early as possible in the design process. Is there a concern that the lack of detailed information early on will lead to poor advice or poor results later on?
Yeah, it's definitely a concern, and it requires that your simulation and analysis team knows what they're doing, so to speak. It's important that they've got their heads on straight about the advice that they can give at the early stages and what they can't give. And it really is about kind of taking broad approaches and then narrowing down in sort of detail and accuracy as the design process goes on. So some of that early simple box modeling that I was talking about, is looking at very big moves around the building. What is the impact of floor to floor height on our anticipated heating energy demand? Does the building need to thermally break any balconies that it's putting outboard? The ability to answer those questions early, again, it sort of sets those design bumpers, and then as we move down the design process, we can narrow them to make sure that we're staying on target to hit our goals of carbon neutrality.
Okay, now how do methods for assessing some of the potential passive design strategies that you have described, such as daylighting and natural ventilation, differ from the early to late stages of design?
Yeah, so that all plays again into that whole sort of narrowing of sort of the design envelope, so to speak. For something like daylighting, you might be initially just looking at a bulk parameter like window to wall ratio or visible transmittance of your glass to just see roughly what percentage of a open floor plate will have access to usable daylight throughout the year. When you've optimized for that, when you move into detailed design, then it could become, a much more specific look, not unlike the case that's illustrated in this slide, where we were really looking at specifically, what the dimensions of the individual windows would be for a specific office bay, and how they were arranged between, clerestory glazing and vision glazing down at the eye level. So it really kind of takes you need to start broad and look at what big moves you can address early, and then really try and figure out a way to winnow that down into a more specific and detailed analysis case to assist the design team.
Okay, great. Thank you for that. Just a few questions from the chat. Tyler B says that was a very informative presentation. Well done.
Thanks, Tyler.
Sam says, hi, how Intuitive works with architects in the concept stage in analyzing embodied carbon.
Yeah, well, I mean, it's coming fast and new, really. I mean, the development of carbon as an early stage analysis tool has really only come up in the last year, so it's very new. But we are finding that some good response from architects, that it can be really useful to have that kind of approach of just even querying some basic design schemes in the early stage to get an idea of how to be on the right footing. Another real benefit of that type of analysis is that I focused a lot on the embodied carbon by element outputs of it in terms of slabs versus footings versus cladding, but also in terms of material type. So if you know that concrete is your biggest driver, is there an opportunity to use alternative cementitious materials or Portland limestone cement instead of a traditional Portland cement to reduce the embodied content of that concrete, knowing that it is your most significant material? Same story for steel. Are there ways to engage recycled or more local sources to be able to, again, reduce that embodied carbon, so that even then the design itself hasn't particularly changed, but the sort of ingredients that go into the individual components have been optimized to reduce embodied carbon.
Okay, that's great. Okay, we have a few more questions here. So we have one question from Samer. There is a persistent issue with using environmentally friendly and sustainable interchangeably. Why can the industry adopt a more comprehensive that addresses all the pillars of sustainability and not only the environmental performance?
Well, I can't speak for the industry as a whole. I think that question is trying to get at the aspects of wellness, economic sustainability, as well as sort of social sustainability for societies. I can't really speak to how to influence those other factors. Certainly, there are nice intersections between a well-designed building from an energy performance point of view and thermal comfort, which greatly improves wellness for the building occupants. And I apologize if any sort of use of environmentally beneficial and sustainable, if that sort of crossed any wires or confused anybody out there. Essentially, it's all just driving towards the idea that reducing carbon from our total life cycle carbon from our designs as rapidly as possible is the goal that my work and the teams that I work with are focused on.
Okay, and just a little other follow-up to that question. I think you might have answered it, but I'll read it anyways. What to focus on carbon and overlook other environmental performance metrics, such as acidification of ozone depletion? I think you kind of just answered that as well.
Yeah, no, these are it's in some ways that you're seeing a presentation by a hammer who's telling you about a lot of different nails. This is really the purview where I can work, but you're entirely right, and especially from that life cycle impact and embodied carbon point of view. There are any other number of things that are listed in an environmental product declaration of potential negative impacts of what materials you select, from things like acidification, eutrophication, which I believe is excess nitrogen emissions that causes algae blooms. So there is a series of other environmental impacts that come from materials. This presentation was specifically focused on carbon because it tends to be the most pertinent, present, and immediate need that needs to be addressed. But at the same time, that is not to say that any of those other impacts should be ignored, swept under the rug, or overlooked. It's that silver buckshot approach, not silver bullets. We need to figure out how to solve all of these impacts that we're making, and it's going to take all hands and lots of smart people working in all different directions.
Okay, that's great, Tristan. And we have a couple of great comments here from Ahmed. Good job, Tristan. Very informative session. And from Patrick, great session. Thanks, folks. Thanks, Tristan. So great. I think we'll end it here. I think that's all the questions that we have. So I'd like to thank you, Tristan, for the presentation. That was great.
Thank you, Erica. And thanks to everybody who stayed on the line and for all the great questions. Feel free to look me up on LinkedIn and reach out if you have any other questions that you want to ask. Okay, that's great. That's great. So now I'd like to just thank everybody again for attending the session. And I'd like to also thank CanBIM and SASBIM again. That's great. Now, this session will be recorded and it will be available to everyone on the canbim.com website.
And if you'd like to find out more information about future events that CanBIM hosts, you can join the mailing list from the website, or also check out the website at canbim.com for future events and initiatives. So next up on the schedule is going to be at 11:30 a.m. Eastern. It's going to be an executive session, Sustainable Business Models with Tim Coldwell, President of Chandos. So thank you very much, everybody, and have a great day.